I'm still paying you. I got the hard ass beats like the crack of the tech. I'm still paying you. Think y'all forgot what rap sounded like? I'm still paying you. Back to match up beats, the bang of the average. I'm still paying you. I'ma make y'all pay for the dues.
Okay, so as I said in class last week, I can't be on campus this week. I'm in London, and actually right now we are actually in the emergency room here in London. So Fat Face Rick did a microdata of LSD last night, went walking around, and then he got beat up by a bunch of like 12-year-olds. They basically beat the shit out of him. So we had to bring him to the hospital, and I'm out here in the waiting room waiting him to get cleaned up, stitched up, and then we can go back. So I figured while I'm sitting here, we have to teach about databases because that's it's super important in life. So let's jump into this. So last class we were talking about SQL, and then today we're not going to start talking about how to actually build the system. So as a reminder, Project Zero is due this coming Sunday coming up. Again, you're required to pass that if you want to get into the class. And homework 1 is also due this coming up Sunday at the same time. So now that we understand what SQL looks like at that sort of logical level, like how to define tables, how to run queries on it, and what are the properties of relational algebra and how that fit into the relational model, that's sort of the last time we're going to be looking at the application level of a database for most of the semester. Now we're going to really start talking about how you had to build the software to run the queries that we saw or store the data that we want to put in the database. And so that's really what's going forward at this point in the semester going forward is like, actually, how do we actually build that system? And so the outline of the course roughly looks like this. So we've already sort of covered what the first week of the relational database looks like. And we're now going to go sort of at a level by level basis and start looking at like, okay, here's how you build the different layers that you need to put together and interact with them to actually build a full-fledged database system. And so this is sort of the rough outline of where the course is going for this semester. A lot of the things we'll be getting to at the very beginning will be like how to build a single node system. And then once we understand that, then we'll finish up and talk about how can you scale it out and run across multiple nodes. And so the way to think about this is the database system is essentially a bunch of layers where there's a well-defined API that one layer exposes to the next layer in order to provide certain guarantees or certain operations on data or whatever the level of the level that they're trying to interact with. So you can think at the very bottom, you have this disk manager, the thing that actually reads and writes data from disk, because essentially a database is just files on disk. And then above that, you have the buffer manager that's going to be responsible for bringing in pages from disk, bringing them memory, and then handing them out correctly to the other components, such as access methods, who are then accessing data on behalf of operators that are executing queries. And above that, we have a query planner optimizer to try to then take SQL queries and convert it to physical plans that we can then execute in our system. So again, you just think of the database system as a bunch of layers, and what we're going to be going through this semester is actually we're going to go start at the bottom and work our way up the stack. So the application is up here. This is what we talked about before, like the relational database in SQL, right? And it interacts with the front end. That's going to be the query planning. And then we're going to talk about how to go up the stack now and be able to execute those queries. So today's class, we're going to actually start at the very bottom. We're going to talk about storage. Next class, next week, when I come back in town, we'll actually go back up to the buffer manager, talk about how to bring some pages of memory, but then we actually need to go back down and talk about different alternatives to storing things on disk. So that'll be where we're at for the next 2 weeks. So today, again, so we're going to start talking about what the background is of what the database is going to see and interact with in terms of hardware. Then we'll talk about the lowest level, actually how to store things in files, how you then divide those files into pages, and how you then divide those pages into tuples. So today's class is going to be what I call a row-oriented centric view, meaning we're going to organize the data, tuple says in rows. We'll see in 2 weeks how we actually flip that on its head and actually store things in an alternative way. So today is sort of a classical database system architecture, how the original ones were built in the 1970s, and then we'll go from there and talk about how to, alternative methods, the more modern methods in a few weeks. We kind of understand the basics first before we get to the other ones. Okay. So the other thing about this class too, I also bring up is that we'll be focusing on what I call a disk-based or disk-oriented system architecture. And what I mean by that is that the software system, the database system is going to assume that the primary storage location of a database will be on non-volatile disk, like an SSD, network storage. It doesn't matter, but it's considered volatile. And then it's a classic von Neumann architecture where you can't operate on anything that exists in disk. Instead, you have to bring pages from disk or the files from disk into memory, into volatile storage, like something like DRAM. And then that's where you read and write to the data that you want. And the data system is then responsible for writing up those changes to the non-volatile disk at some later point. So this is really what we're going to be focusing on. And then all of the components that we're going to talk about, the hours that we're going to talk about, is going to be predicated on this architecture assumption. So the way to think about how we're going to interact with non-volatile and volatile storage is sort of this classic hierarchy like this. You've probably seen this in other classes, right? Should not be anything new. But you sort of think of the bottom layer, you have the very large but slower storage, and the very top you have the very fast and cheaper one. Right, so the top would be things like CPU registers, because that's the smallest amount of data you can store or access on a CPU. And obviously it's going to be really, really fast, but it's also going to be really expensive. It's going to be very limited. And then as you go down the stack, things get bigger, capacity is larger, they're going to get slower, and they're going to be actually much cheaper to store per byte or per gigabyte. So this is the sort of the way we want to think about and how these different storage layers are going to work with each other. But there's also this division line that I'll draw here between DRAM and SSDs, and basically say at the top you have, again, what I call volatile storage, where, again, if you lose the power on whatever the computing device you're using to store this, everything gets blown away. But they're going to support what I'll call random access or byte addressable access, meaning we can jump to individual byte offsets without worrying about bringing in a bunch of other data that maybe we don't actually need. Now, with cache lines on the CPU, that's not entirely true, but for our purposes in this semester, we can ignore that. And then below this demarcation line, we have non-volatile storage. So this will be things like, again, spinning disk hard drives or SSDs or network storage like S3 on Amazon or Google Cloud storage and so forth. So these devices will be non-volatile, meaning if you write to them and we can send a command to say, flush the data to this storage device, and then we'd be guaranteed that if power is lost, that we come back and data will be there. Again, if obviously the machine catches on fire and the disks melt, we can't do that, but there's ways to get around that. We'll cover later in the semester. These devices are also going to be what are called block addressable, and that means that the smallest granularity in which we can access data is going to be through a block. And typically this can be 4 kilobytes, sometimes larger, sometimes smaller. But we can't do the byte addressable access that we can do in DRAM or CPU caches, meaning if we want to access a single byte, we have to bring in the whole page or block where that byte resides, even if you don't need that other data, right? And that's sort of the trade-off we have to make in our system design when we actually want to start storing things on non-volatile storage. So for the purposes of this semester, what we're going to say is that anything below this demarcation line here between non-volatile and volatile storage, we're just going to say that's just called disk, right? Well, it doesn't matter whether it's an SSD or spinning disk hard drive or network storage. Even below network storage, you can have things like tape drives, but people really only use that for archival stuff like Amazon Glacier. So everything down below is block addressable and non-volatile. We'll just call that disk. And then above that line, we're going to say that we're just going to call whatever's in DRAM, we're just going to call that memory. And then above that will be anything that's like directly on the CPU, like on the actual die of the socket itself, like CPU caches and CPU registers, right? We're just going to say that's CPU storage. And so for the purposes of the semester, we're actually going to ignore CPU-related stuff. We can talk a little bit about more efficient ways to more efficient ways to store the stuff, but like for our purposes here, we can use it and all that, right? We'll cover these things in the advanced class because that's where we really care about like cache locality and other things. But for this semester, it's really about, is it in memory or is it on disk, and then how do we move back and forth. Now, the other thing we have to be mindful of too, and this is going to be where we're going to deviate from maybe traditional algorithm classes you've taken in computer science classes before, where we actually need to be aware of how long it's going to take for us to access data at these different levels. And so there's this great table here that comes from this website you see in the corner. Jeff Dean has a version of this. It actually predates him and goes back to Jim Gray from the early 1990s. But basically, it's a table of like, here's all the time it takes to access different levels of storage, right? From the non-volatile ones, the volatile ones down to the non-volatile ones. And here I'm showing these numbers measured in nanoseconds. So it basically just shows like if I'm going to read something from DRAM, it's going to take 100 nanoseconds. But if I'm going to read an SSD, now it's going to take me 16, maybe 50,000 nanoseconds, right? So it's like 2 orders of magnitude slower than reading some DRAM. So obviously we want to be mindful of like when we're going to read things from disk and try to minimize the amount of time how many times you get to do that. Then once you get below an SSD, that's when things just get like super, super slow. So I realize as humans, it's hard for us to wrap our heads around times in terms of nanoseconds. So there's a really easy trick that Jim Gray came up with, where if you just replace nanosecond with second, then you really start to see how expensive these things are going to be relative to like reading data that could be in memory. So if you read something in like L1 cache, that would take a second. So that's like if I want to read a book, I can just go over to that chair there and read a page in the book, and it would take me a second or 4 seconds. But then if I want to read something in a tape drive, it's going to take 31 years. That's equivalent of like me flying to Pluto and back to read a single page in a book. Right? It'd be ridiculously long. You want to try to avoid that as much as possible. Right? So again, as I said, most systems are not going to be stored in tape drives, so that's not, you have to worry about that level of latency. But certainly there's a lot of systems, and real systems today are storing these SSDs, spinning those hard drives, and network storage like S3. And so we got to be mindful of like, when are we going to read and write data from disk, and try to avoid having to block the system while we're waiting for those things. The other thing we need to also be mindful of in our implementation, our algorithms, is the difference between sequential and random access, or random I/O. So again, when you assume you're talking about quicksort algorithms in intro classes and so forth, you just assume that, I can read and write anything in memory, and the time it takes to read any object or entity takes the same amount of time. But in reality, of real hardware, the latencies between random access and sequential access can be quite significant. So random access would be like I'm jumping around to different locations and reading different bits as I need it, or bytes as I need, whereas sequential access would be read like a stride of data that is contiguous with each other, and so I can just do one lookup and get multiple bytes or kilobytes that are all close to each other. So just to give you some ballpark numbers here, random I/O would be on a fast SSD, maybe 80 to 100 microseconds. So let's be on the high end for like a consumer grade drive, where sequential I/O would be, you can read a bunch of data in terms of 10 to 100 microseconds. And again, it depends on like how much data you're reading, how many threads are reading. This is all a bunch of complicated that we're not going to really cover in this class. But the main thing to begin to be mindful of is that like there is a huge difference between sequential and random I/O, especially when spinning these hard drives. And we want to try to maximize the amount of sequential access we can do whenever we have to read and write anything from disk. And that means that we'll make certain choices in our algorithms that try to reduce the number of writes to random pages, so that we store data in contiguous blocks. And that means there'll be certain systems will do certain things that seems like crazy to do. But again, if you're aware that like sequential access is much faster than random access, it would sort of make sense. So like MySQL, for example, will they'll store their when they write dirty pages to disk, they'll first write it to this double write back buffer, and that's a sequential write where they put all the dirty pages they want to flush out. They write those sequentially. Then in the background, they'll do the random writes at a later point. But at that point, you're not blocked waiting for that dirty page to be written because you've written that sequentially the first time. All right, so the ultimate goal for our database system, we're going to try to build this semester, is a system that can manage a database system that's larger than the amount of memory that's available to the system. And so if you only have 8 gigs of RAM, you can run a database, handle a database that's 16 kilobytes or 32 kilobytes or gigabytes or larger. Right? So the challenge, of course, is going to be to provide this illusion is that we have to move data back and forth between disk and the memory, right? As I say, sort of the von Neumann architecture. And so we want to do this in a clever way and take advantage of many optimizations as we can, where we want to avoid large stalls while we're fetching things from disk and have the system sort of grind to a halt just because we're waiting to go fetch I/O. And so there'll be a bunch of things we'll do as we see go along about allowing multiple queries to run at the same time, reusing data that we bring into memory, being clever about what we write out, back from memory into disk. So there's a bunch of things we're going to want to do, and we're designing certain algorithms in such a way that we can reduce that burden, reduce that cost of having to read my data from disk, and again, make it look like we have enough memory to handle everything. And of course, at some point, if the working set size of the data of all the queries that are running, meaning all the things that you need to be in memory is larger than the memory you have, that's going to be a problem. There's no way to get around that. But for other sort of, in the general case, we'll be okay. All right, so everything I've said here is kind of hand-wavy and vague. So let's actually go into more details of look at a high-level picture of what a disk-oriented database system is going to look like, and then we'll see what we're trying to then design and build as we go along through the rest of the semester. So, as I said before, the database and a disk-oriented system, it's just showing files on disk. Sometimes it's one file, like some systems like DuckDB and SQLite. They pride themselves on storing everything, the entire database as a single file. But most systems are going to store the database across multiple files on disk. And these files aren't special in terms of the operating system, meaning it's like the operating system just uses a bunch of files that it's created with fwrite or fopen. Is really the data system interpreting what those files are, where the sort of important stuff or the magic happens in the system. So we have on our non-volatile disk, we have some kind of database file, and we're break this up into a bunch of pages. And these will be sort of fixed length size segments or divisions of the file, and at the header or at some special location, usually, but usually the header, there'll be what we call a page directory, and that's just the kind of internal database of keeping track of here's all the pages that I have on the disk. And then now I have in memory for my data system, I have what I call a buffer pool. Sometimes it's called the buffer cache or the memory cache or something. They're all different systems call them different things, but it's basically the same thing. And this is going to have a bunch of frames, we'll call them, where I can store pages that I'm going to bring into memory. So again, the database system's job is really about managing the movement of disk pages back and forth between disk and memory in order to service whatever the queries are that I'm executing.
Page number 157. Please go to position 4.
It's not us, okay. So I have my execution engine, right? I'm not defining what this is for now. We'll just assume there's something above that wants some queries. And so it's executing something that says I want to get page number 2. So at the very beginning, assuming that nothing's in memory. So the very first thing we need to do is to bring in the directory to memory, because the directory is going to tell us what pages we have and where to go find them. And again, for us right now, in this example here, we assume it's a single file, but it could be spread across multiple files and multiple directories, or even across multiple machines. But at this point, it doesn't matter. So we bring the directory in, and we're going to look inside that, and that's going to tell us where to go find page 2. Right? So for simplicity, assume we can just compute whatever offset is in this file, and then it finds it for us. So then we go fetch that page into memory, and then now we then hand back to the execution engine a pointer to that page in memory, and the buffer pool is going to guarantee that that pointer is not going to get replaced or swapped out with another page until the execution engine says they're done with it. So now, also notice here that we didn't say anything about what's inside these pages. It's up to whatever's up above in the system to then interpret what's in these pages is to decide what the bytes actually mean. But this lowest level here, we don't know, and we don't actually care right now. So then the execution engine does whatever it does, interprets the page layout, and let's say that's doing an update. So it wants to update the contents of page number 2. So then it writes back the change to the page, and then it can then say I completed. And at some later point, the buffer pool is going to write out that dirty page to disk and update the files. And it does it in a way that's safe, so that if we crash and come back, we don't lose any of those changes that the execution engine made to that page. So we're not going to go into the details of all these things in this lecture. We'll discuss things in other lectures, but we'll discuss some of what these pages actually look like at the files in this lecture, and then we'll come back to this in 5 and 6. And then we're going to spend, in lecture 4, we're going to spend time discussing what this buffer pool manager looks like in memory, and how it does some of the writing out to disk. We won't discuss everything, how to do this in a transactionally safe manner. That'll be later in the semester after the midterm. But we'll just have a general idea of how the mechanism is actually going to work. So we'll cover that in next week in lecture 4, because also too that'll be what you'll need in the first project. And then for what the execution engine is going to look like, we'll cover that in lectures 13 and 14 in a few weeks. Okay. All right. So there's 2 big questions we have to deal with in our system. The first is how we're going to represent the databases, which are files on disk. And then the second question we have to deal with is how we're going to move those pages back and forth from disk into memory, and then hand them off to other parts of the system in order to interpret their bytes. So for today's class, we're going to focus on this. As I said, next class, we'll then come back to problem number 2 and understand what the buffer pool manager is actually doing for us and how it works. So, as I said, the database is just files on disk, and there's nothing special about them in terms, again, what the operating system sees. It's just as if I, create a bunch of files in any application, and then the data system is up to interpret what's in them. Now, historically, these file formats what's in the files has always been proprietary, meaning like they're specific to whatever the database system that created them, and they're not usually interpreted by other database systems. So like you can't take a Postgres file, like its file format, and then open it up in MySQL or Oracle, right? It's not going to know how to interpret those bytes because it doesn't mean anything to the other system, right? There's a newer trend in building what are called portable file formats, things like Parquet, where it's a file format that is open,
Number
an open spec,
158.
and that any system can read and write to them. But we're not going to discuss that in this class. We'll cover that in a few weeks when we talk about column stores. The other thing also to point out too is that the database system is typically going to run on off-the-shelf file system like ext4, WinFS, whatever the operating system installs, and that's going to be typically good enough for what we need. There was some systems in the 1980s that would actually build custom file systems on top of raw block storage. So you'd buy like a storage device as just raw blocks, and then the database system would install its own custom file system inside of that. You typically don't see that, especially in non-open source systems. And you only really see this in like sort of really high-end enterprise systems like Oracle and Teradata. Most people aren't going to do this. Right, so if you look at Oracle's documentation, you could have this thing called Oracle ASM. It basically says like instead of having the operating system manage the file system for you with a logical volume manager, whatever, instead the data system is going to do that for you. It's basically injecting a custom file system to the operating system. That still exposes the standard POSIX API that the operating system expects, but it lays out data in such a way that it's very specific to what the data system wants. There hasn't been a study on this for a while, but you get roughly about a 15% improvement in performance for this. It's a major engineering effort, and most systems aren't going to do this. All right, so then the data system at the lowest level is going to have this thing called the storage manager. Again, sometimes it's called the disk manager, but it's usually the same thing. But it's the component of the system that's responsible for reading and writing data out the disk. So again, you could rely on the OS to do some things, but you don't have to do everything. And most of the higher end systems, the better systems, are actually do their own scheduling for reads and writes and figure out where they're actually going to put data on their own, and don't let the OS kind of just figure crap out for you, because it's always going to do a bad job. All right, and then those files that we're storing, as I said, they're going to be broken up into pages, usually fixed length, within the file. And then some systems will allow you to define a different page size per table. Like IBM DB2 can do this, but still within the single the file itself, so the collection of files for a table, they'll be all the same size.
Number 159. Please go to position 2.
And then the storage manager is going to be responsible for keeping track of these pages, reading and writing to them, and it keeps track of available space. And then when there's a request up above that says, hey, I need to store so many bytes, you can then figure out where's the free space to actually store this. Now, the other thing we be mindful of is that within a single files on disk, where it's like a single instance running on a box by itself, we're not going to maintain multiple copies of a single page on disk, like at a physical level. At a logical level, we may have multiple copies of data within a tuple, because we might store them in the heap files, which we'll talk about in a second, and then store it again in the log file. But it's not the storage manager's responsibility to I got to write this page out, I'm going to make multiple copies of it. That's either going to happen at the level below it, like in the file system, like with something like RAID, or like a storage appliance that can make multiple copies, or have replicas like an S3, or it's going to happen up above the storage manager, where there will be something that says I have to have logical copies of this data across multiple nodes. All right, at the lowest level of the storage manager, it's not going to do that. It's really about I got to write data to a single, a single instance, or a single location for a single page. All right, and then as I said, the page is going to be a fixed size block of data, and that's going to basically contain everything that's in our database system. Right, so it's going to contain the tuples that are in the data. It's going to contain metadata about those data, the catalog about what tables I have, what information I have. The page directory is basically stored as pages as well, indexes, log records. All this is going to be stored and broken up into internally as pages. Now, most systems are not going to mix the page types, meaning you're not going to have within a single file pages for table X and table Y, or index X and table together. It's typically going to be here's one file, it has data just for this one page, right? Some systems are also going to require the pages to be self-contained, meaning everything you need to know about what's inside the page has to be stored in the page itself. So you can imagine things like, if it's a data page for a table, you would say, here's all the metadata I need to have to know that this page is for this table. Right? You do that for crash recovery, but you only see that in something like Oracle, where they're really paranoid about not losing people's data, and rightfully so. The other important thing to know is also that each page is given a unique identifier called the page ID. And a page ID is going to be this unique number that the data system is going to maintain to keep track of, here's how to address and find this particular page I'm looking for. And it can be unique per the database instance, per table, per database. But it's going to be some number that's going to tell us where to go find to help address that single page. Now, it could be an offset in the file as well, but it could just be also a logical location that would then use the page directory to go then find out where that thing's actually being located. So now, important thing to understand also is there's actually three notions of pages in a system. So at the lowest level, you have what's called a hardware page. Right? This is typically 4 kilobytes, and it's the smallest atomic unit of data that the hardware can guarantee that it can write out to the storage device, the actual physical medium of the storage, that's done atomically, right? So this would be, if I have to write out, say, 2 4 kilobyte pages, or 8 kilobytes, the hardware can only guarantee that it can write the 1 4 kilobyte atomically. So it can't guarantee that it's going to write out both pages or none of them. It has to guarantee that it can only guarantee that it can write one of them. All right, so then now above that, you have the OS page. And by default in Linux, this is 4 kilobytes. In new versions of Linux, and you can get what are called huge pages, and then you can do like 2 megabytes, 1 gigabyte. But this is basically the mapping of a hardware page to a logical page that the OS is going to keep track of in its own internal page directory. And then now above that, we have the database page, and this is going to be what the database is, how the database is going to organize its own pages. So again, the hardware page is always going to be 4 kilobytes, and that's the largest block being guaranteed to be read atomically. But then the OS can have its own page sizes, and the database can have its own page sizes as well. And we just have to be mindful of how we're going to do this mapping from a database page to a hardware page, and be aware of that if we have to write more data that we can do atomically in a 4 kilobyte page, we have to do a bunch of extra steps to make sure that things are written safely before we tell the outside world, before everything has been flushed. So the database page size is going to vary per system, right? On the smallest, actually, with something like SQLite, I know for some embedded devices, it can go down to 512 bytes. By default, it's 4 kilobytes. Oracle, by default, is 4 kilobytes. The DB2 is 4 kilobytes. RocksDB, which is a embedded storage engine that's used in a lot of systems, that's 4 kilobytes. WireTiger is the storage engine for MongoDB, that's 4 kilobytes. Then you have things like SQL Server and Postgres, right? They're 8 kilobytes. And then MySQL famously can go up to 16 kilobytes. So the size of a database page, what you actually want to use in your system, depends on many different factors, like the environment, the hardware environment the system is running in, what the data it is you're actually storing. Like, are they really wide tables that have a lot of columns, or a small number of columns? Are they big blobs of data, or are they just small integers, right? And it actually depends on the workload you expect to run in your database system. So in general, for data systems that are doing read-heavy workloads, and we'll see more about this in a week or two, where these ones you actually want to store things as larger page sizes, because you know you're going to do a lot of sequential scans where you're reading a lot of data that it's all contiguous. So for every page I have to read, I'm going to bring in tuples that I know I'm going to want to, that I need for my query. So every fetch for a page, again, a database page, brings in useful data for me. We'll see how we handle that when we switch from a row store to a column store. That's going to be one of the big things that they're going to do. And then for systems that are more write-heavy, meaning like I'm doing a lot of like updates to tuples, like updates and deletes and inserts. These ones you typically want a database page in the 4 to 16 kilobytes, because again, the non-volatile storage is block addressable. So that means like if I only have to write, if I'm only updating a single byte within a page, I have to write that whole page out. So if it's a 4 kilobyte page and I don't update a single byte, I still have to write 4 kilobytes out to disk. So I don't want really massively large database pages, because I would have to write all of that out. I can't just do like sort of fine-grained updates on things. So for this class, we'll start off with just talking about 4 to 16 kilobyte pages. When we talk about in lecture 6, we'll see then why larger pages can make a difference when we do read-heavy workloads. All right, so now there's a bunch of different ways we can manage these pages that are on disk, and again, they're all going to have different trade-offs. So how we do certain things. So the heap file will be the most common one, the basic ones we'll see, and we'll assume we're doing that for this lecture and next lecture. We just assume a bunch of pages, and I can address them and bring them in, and they're not ordered anyway. Another approach would be a tree file organization, where I'm storing the pages in a tree data structure, and as I traverse the tree, I'm bringing in pages as I would need them. And we'll talk a little bit about that later on. Again, for this class, we don't need this. Sequential organization, or security file organization, sometimes called ISAM. This is an older architecture from the 1970s that people really don't do anymore. But it's sort of similar to the tree one. We don't have to worry about this. And then hashing is another variation similar to a heap file, where things aren't in order that you can jump around into them. Right. So I guess that for this lecture, we're going to assume we're doing heap files, and then for the most part, right now, for the next few more slides, we don't have to care about what's inside the pages, and then we'll go into more detail what they look like. But just understanding what the page architecture looks like, it doesn't matter what's inside them. So a heap file is going to be an unordered collection of pages, where, again, because SQL is unordered, the relational model is unordered, we can store tuples anywhere we want in random order, just wherever we have free space. And then it exposes a basic API to create, get, write, and delete pages, because that's the basic operations we need to do at this lowest level in the storage manager. We also need to support being able to iterate over all the pages, meaning like give me the page IDs for all the pages on a given table or given index, because we'll need that to be able to do a sequential scan. But when we do like looking up things in indexes, we'll see how we get the page ID from an index lookup, and then we need to be able to go get that single page. But also we need to be able to scan across all the pages as well. So for this means that, again, we need additional metadata, essentially what we had in the page directory, to keep track of the location of these files, and also keep track of where do we have free space. Because anytime we need to store something, we got to say where can we put it. And since we're going to assume that we're storing things like 8 kilobyte pages like it is in Postgres, most tuples aren't 8 kilobytes, so we need to make sure that we can fill in free space that we have, and our data doesn't balloon to be too big. So here's a basic configuration. We assume a database is a single file. So assume something says, hey, I want to go get page number 2. I'm not defining how I'm doing that just yet. There's some part of the system that says, give me go page 2. I can just do simple arithmetic to say, I know the starting location of my file, I know my page number, I know my page size, because again, I'm assuming all the page sizes are the same on disk. And I just do simple math to be able to say, jump to the offset that I want to find the thing I'm looking for. In cases where the database is broken up across multiple files on disk, right? Now we want to get something like page number 23. Again, there's this page directory thing where we haven't really defined that's going to have the metadata we need to go find the file that may contain the page. And then once we get in there, we can then do simple math to say, for a given page number, what's the, and a given page size, what's the offset I should jump to find the bytes that I need. It's a pretty basic architecture. And again, different databases do different things, how they implement the page directory, but at a high level, all these systems basically work this way. So a common architecture is to use what's called a page directory, as I sort of talked about before. And this is just like a database within the database that keeps track of, here's all my pages that I have for sort of logical database objects, right? You could break it up across different ways. Like you'd have if your data system supports multiple databases, you could have a directory per database, you could have a directory per table, per index, or whatever, right? Different systems will do different things. But the basic idea is that I have a way to say, if I want to get data from like table X or table Y, here's the file, here's the directory, here's the location on the network that has this data. And then within that, I can then jump to the offset that I need, that based on the page directory information about where to find the pages that I'm looking for. Now, the tricky thing is going to be is making sure that this page directory is synchronized on disk with the data pages, because if we crash and lose this thing, we're kind of screwed, because now we don't know where to find anything else. And then if we start allocating new pages for our files, we want our page directory to sort of reflect that. Now, the truth is, it doesn't actually have to be 100% always synchronized, because if you crash and come back and this thing gets trashed, if you have enough metadata in your files, you could actually recreate this. It just makes recovery a lot slower. And a bunch of systems are going to have different ways to do this more efficiently. But in general, this is something we want to keep synchronized if we can, at least in memory, certainly in memory. But on disk, we can kind of be a little bit looser than we would be maybe other data, right? It's a trade-off between how fast you want to run at runtime versus how long it takes to recover if there's a crash. So this, we can keep track of additional metadata about, for every file, how much free space we have on a given page or a given file, what are pages that we have that are completely empty that we can jump to them fairly quickly, and then keep track of like are these pages keeping track of metadata or about a table or index or whatever, or are they keeping track of like actual user data, like for tuples? And the page directory can maintain all this information for us. All right, so that's what things look like on disk. You can assume that the database is a bunch of files that broken into pages. So now let's talk about actually what the pages actually look like on the inside. So in general, at a high level, every page is going to have what we'll call the header, where we keep track of metadata about what's inside the page. So obviously, you keep track of things like the page size, a checksum about the contents of the page, the version of the software that wrote that information, right? So that way, if you upgrade the version and change the layout of pages, you know whether this page reflects that new layout or not. There's much information we can maintain about transaction visibility, meaning like what data should be visible to what transactions. For that one, we don't have to worry about this class. We'll cover that again after the midterm. It could have additional data information about like how the data is actually being compressed, what encoding they're using to store things. In some cases, like in Oracle, we had said they had to be self-contained. So actually contain the table schema in the header of the page as well. So if there's a crash, you can come back and actually just look at the page and say, I know what table this belongs to. Here's how to interpret the bytes that are inside of it. Sometimes you'll see also summary information or sketches that keep track of like here's the values that I have inside my page. So if I don't maybe have to scan the entire page and look for certain pieces of data. Like I'm looking for all records that or all tuples that have the name Andy in it. If I have a summary in my page that keeps track of like the number of Andy tuples inside of it, I can just read that. If it's 0, then I know enough through the rest of the tuples. It's a high level idea of how the summary stuff works, and you only see that in the read heavy stuff. We'll cover later. The checksum is super important because if you crash and come back and you read the page back in, or actually not even a crash, just go read a page in. You want to know whether I got corrupted on disk, whether you can trust the bytes you're reading. So the checksum will tell you that. Again, different systems will do different things. And it's the enterprise ones that'll have the more safety controls in place to make sure that you're not losing data or corrupting data. Okay, so then now within the page, we want to figure out how we're actually going to store tuples in it. Right? As I said, at a high level, there's always going to be a header. But then now we want to talk about how we actually put tuples inside the page or put data inside the pages. Right? Assume we're doing tuples. We won't worry about indexes for now. That'll come later. And then we're also going to assume that we're doing what's called a row-oriented storage model, meaning we're going to organize each record or each tuple as a row where all the data is being stored contiguously inside the page. And that means also we're going to assume that each tuple has to fit inside a single page. We'll see how we handle larger values in a second. But for our purposes here in the discussion right now, we'll just assume that every tuple is contiguously stored within a single page. So there's actually 3 ways to do this, to organize data into pages. So for this class here today, we're going to assume we're doing tuple-oriented storage, meaning the entire tuple is stored in its entirety in a page. But there's actually 2 other methods we'll cover next week, next Wednesday, called log structured and index storage, where we're actually going to store not the tuple, but we're actually going to store basically the delta of a tuple when things get changed. And we have to end up having multiple copies of a tuple if it gets updated multiple times. And that'll make more sense when we talk about it later on. And index organized storage is basically storing, as I said, the data as a tree structure. But we'll come to that later. For our purposes here, assume that there's only one copy of a single tuple, and it's going to be stored in a page in its entirety contiguously. Okay, so if we wanted to start doing this, how should we keep track of the tuples in a page? Well, we could just do something really simple. We just say, all right, I'm assuming that the tuples are all the same length, and then I'm just going to append the tuples to the first 3 locations that I have in the page, and I just have my header and just keep track of the number of tuples that I have. So I can do simple math to say, at what offset do I jump at the page to find the data that I want. So just every time I insert a new tuple, it's appending it one after another in the page like this. So now if I delete a tuple, well, that becomes a more tricky, right? So if I delete tuple 2, now I have the number of tuples to 2, so I can't just jump to the end anymore, because I need to make sure I don't overwrite tuple 3. So maybe I can just do a quick scan and try to find the first free slot and then put my tuple that way. But then this art starts to get kind of expensive. If I have to scan every single time, and furthermore also too, I can't do any compaction now, because if I move tuple 3 back to where tuple 2 slot was, or location was in the page, then I had to update a bunch of other metadata or index data structures, because now the physical address of tuple 3 would have changed in my page. But then also this doesn't work either if I have variable length data, because now I may have much of free space that I can actually use to insert the new tuple that I need, or I'd have to start moving things around, again pay that penalty of updating indexes or updating other parts of the database system. So to overcome this problem, we're going to use a technique called slotted pages. And so what I'm describing here is basically at a high level how any row-oriented row storage or tube-oriented system is going to do this. The exact details of what the metadata is storing, or whether the slot is in the beginning or the end, it varies per system. But at a high level, this is basically how they work. So what's going to happen is that we're going to have at the beginning of the page, we always have a header, because it tells us, again, the metadata about what's inside the page, like a checksum and so forth. But then I'm going to have this slot array, and it's going to be a fixed length array that keeps track of a offset within the page for a tuple at a given slot. And at the bottom of the page, that's where we're going to actually store all my data. And so this is going to be any fixed length or variable length data for the tuple, or my tuples. They're going to be at the bottom. And so the slot array basically is giving us pointers or locations or offsets within the page. Like if it's 4 kilobyte offsets, then the 4 kilobyte pages, the offsets aren't going to be that big. And it's going to tell me for a given tuple defined by a slot, here's the offset within that page to go find it, right? So as I want to add more tuples, the slot array is going to grow this way, and then the tuple data is going to grow the other way. At some point you reach in the middle where there's no more free space, and then the page is considered full. Now, is it guaranteed to be 100% full occupancy of data? No, right? Because the variable length data down below might not fit exactly, align exactly within and then the page and have use all the data. But in general, this works good enough. And the advantage of this approach is that now if I delete like a tuple, if I do, like, say, tuple 3 here, I can either leave tuple 4 by where it is by itself, and then hopefully another tuple that comes along gets inserted, could fill in that space. Or actually, I can then just move tuple 4 to be the end of this page, or sorry, to the end where tuple 2 ends, and then all I need to do is update the slot array to say the location of tuple 4 within the slot array is now at this offset. And what I get is indirection that allows me to change the location of a tuple within the page without having to go update other parts of the system. So I don't have to go update indexes. I don't have to go tell them, here's the location of tuple 4 has changed. So the blast radius of the modification I do from this compaction is just limited to the single page.
Ticket number 165. Please go to position 2.
And as I said before, also too, that the cost of bringing things into disk is very expensive versus the cost of manipulating things in memory. So once I bring the page into memory, I can change around the contents of this page, doing compaction or not doing compaction, and that's cheap relative to having to read my data from disk all over again. So once it's in memory, I'm pretty much free to do whatever I want to reorganize this page. Some systems like like Postgres won't do it. Some systems like SQL Server will do it, like every time you update a tuple. But having this indirection layer makes a big difference for us, because again, we can change the location of tuples in the page and not worry about updating indexes and other things. All right, so the other cool thing is that not cool thing. Well, it's all cool. It's databases. So another thing we want to talk about is how we're going to identify each logical tuple with a physical location. For this, we're going to use what we call record IDs. Some systems will call them tuple IDs or page IDs, not page IDs, tuple IDs, record IDs, or row IDs. Essentially, the idea is all the same thing, but it's a unique identifier for a logical tuple that stores its physical location or represents its physical location within the database. And so an example would be like a record ID could say like, here's the file ID and the page ID and then the slot number within that page. And then in like other parts of the system, if I want to be able to say what's the index pointing to, what's the record ID or the address I'm pointing to, you would represent that through this record ID. Now, most systems don't store this. Instead, it's derived at runtime based on, as you read the data, right? So looking at a bunch of different implementations, right? So in Ingress has the tuple ID, it's 4 bytes. Postgres has CTID, it's 6 bytes. Right? That's going to be the page ID and the slot number. Like for these systems, they don't actually store this, but you can uniquely address tuples based on it. The SQLite is an interesting one for its row ID because it does actually store it for you, and no matter what you declare as the primary key, like when you call create table, it's going to use the row ID as the primary key. Think of it like it's like a monotonically increasing value, and it uses that because that guarantees that can uniquely identify any given record, even if you don't provide a primary key when you create the table. All right. Now it's important to understand that this is something that will be exposed to you through a database interface. And hopefully, maybe I can do a demo. I want to go back and come back to this and cut this in the video here. But you'll be able to see this through SQL, and sometimes you can address the records through this. But it's not actually something you want to rely on the application because these IDs can change for a logical tuple based on how the data system starts moving data around, right? So you could do compaction and change the physical location of the data. It's still correct because at a logical level, since SQL and relational models are unordered, I can change the ordering of tuples and everything's still correct. The record ID may change, but again, I shouldn't have relied on that in my application code. All right, so we know what files look like. We know what pages look like. Let's go deeper inside the pages and talk about what the tuples actually look like. So at its core, a tuple is just a bunch of bytes. It's a byte array that have a header in front of it. Just like a page has a header, tuples are going to have a header too, that contain metadata about what's in the tuple itself. Now it's not going to typically doesn't contain metadata about like what the schema is because that is done at the page level. And this is why you don't mix page types or mix data within a page because you don't want to redundantly store the same schema or information over and over again for every single tuple in the page. The page header just has that for you, right? But this will have information about like a bitmap of like what columns are null, information about what transactions can see the data or whether they can see that tuple or not. For that purpose, we don't need to worry about. But then the data system is going to maintain a catalog that keeps track of the schema for every single page, every tuple or table, so that when you go read a page for a given table, you know how to then interpret the bytes within these byte arrays for a tuple to say what the data actually contains. So as I said, the header is going to contain basic information like the visibility, like what transactions created at what time, this data, and so forth. It'll have a bitmap for null values. Then everything else of that is just the attribute data. So typically the attributes for a tuple are going to be stored in the order that which you apply them. We'll see some ways you could reorganize them to ensure things are aligned correctly, but most systems don't do that. Instead, they're going to rely on padding to make sure things that are correctly aligned across typically 64-bit values. So let's say we have a simple example here. We have a table foo, and it has 5 columns three integers followed by double by a float. Again, it literally is the byte array for a tuple, which is be stored in the order in which is defined by the create table statement. So now the challenge is going to be is when you have things, again, that span these boundaries, and you need to be clever how you're going to handle it. So for this example here, it's pretty simple, right? I have an ID, 32 bits. I have a value that's big and that's 64 bits, right? And assuming the header is 32 bits, but this will fit nicely within a 128-bit sequence of bytes. So again, if I want to jump now to get this attribute, I just look at I get my offset to the tuple by looking up the slot array in the page, and then now I just do some arithmetic to jump over the header and then jump to this location to find the attribute that I want. And then I basically do the equivalent of reinterpret cast in C++, to then convert the address that I'm looking at to be a 32-bit integer. And this is something that's done at runtime. This is actually a compiler directed. This is actually, there's no computation done here. It's ensuring that any code that comes after this interpretation of this casting here is going to operate on 32-bit signed integer. So now the tricky thing is going to be is when you have data that doesn't fit nicely into these sort of word boundaries, right? For simplicity, we'll assume it's 64-bit words. So the challenge is going to be the table might have smaller types or larger types that might go across these boundaries, and we have problems, right? So this 32-bit integer here fits nicely in the first half of the 64-bit word, but now I have a 64-bit date or timestamp here, and that's going to span 2 words. And likewise, I have now a 2-byte character, which is 16 bits, and then a zip code like this, right? So if things like nicely, exactly aligned, I'm gonna have this problem where now I try to go access something like the date here, the timestamp, right? I got to go fetch 2 64-bit words to go read that in, and some compiler might complain, or the CPU might freak out, depending on what architecture I'm running on, and this become problematic. So an easy way to get around this is just to pad to make sure that everything's always byte aligned. So it's wasting space, but it does ensures that I don't have these problems that I talked about before. So the first case, the integer is for the ID is 32 bits. So I just put another 32 bits of zeros that come after it. The data system knows that anytime it tries to access the data, I only need the first 32 bits, and it just ignores what comes after that. But this ensures now when I do a lookup on the date, I'm jumping to the right location, and it fits nicely within my word. Another approach, you could do this. I've only seen this in the research literature. I don't think any system actually does this. It's just to reorder things so that they're nicely packed in, right? So if I just move the columns around like this or the attributes around like this, then I land with a nice alignment that I would want. Now, logically, it still is defined in the order when they call create table, but physically the bits are moved around, and then it just knows how to do that reinterpretation at the right location to get the data that I would need. Like I said, you could do this. I don't know if any system actually does it. At least I haven't come across any that do this. And then I make sure that the next tuple comes afterwards is nicely aligned. We just put padding after the last one. So again, we still have to make some space, but it's why I said most systems don't actually do this. All right, so now what do the actual attributes look like? So for the basic data types like ints, floats, strings, and timestamps, this is roughly how the system is actually implemented. There could be some variation based on the hardware which you're actually running on, but in general, this is what he would do. So like for a 32-bit integer or a big 64-bit integer, the same way you would represent things in C++ or C, this is what you would get in your system. And that's going to be hardware. It'll be the same across hardware. You do have to worry about NDNS, but for our purposes, we'll assume it's x86. We're not going to worry about that problem. SQLite, talk about this. SQLite actually store everything as strings and then interprets it at runtime. So that way, if you run on a little endian or big endian system, it always comes out to be correct. But most systems do not do that. They do have a little extra work to keep track of like what is the NDNS when they store things, so that if you come back up when a different, if you copy your database to another machine that flips things around, you end up with the data as you'd expect. But for now, we can ignore that. So for floats and reals, for floating point numbers, this will follow what's called the IEEE 754 standard. Again, this is a hardware spec that says how these floating point numbers should be represented in hardware. And again, most systems follow that. Numerics and decimals are fixed point decimals. These are going to be database system specific. And we'll see what they look like in a second. For text strings, either varchar, var binary, text, or blobs, they'll either have things be inlined within the tuple itself. So it'll be like the length of the tuple, or the length of the attribute followed by the actual bytes, or there'll be a pointer to another location or another page that'll have that data that you can follow along. Again, we'll see what that looks like in a second. If the varchars are small enough, you'll store them in line. If they get too big, then you store them in overflow pages. We're not going to talk about this class, correlation sorting, but you do have to be super careful about for text strings, about who's actually deciding, the right way to lexicographically store data. For different languages has different orderings, and data doesn't have to worry about that. But for our purposes here, at this lowest level for these bytes, we're not worried about that. We'll talk about that later when it comes to sorting, but it's something we need to be mindful of. And most things, by default, some systems will store things as ASCII. You now have to worry about Unicode or UTF-8 or UTF-16, so you may store things as that as well. Like, it's gotten more tricky in recent years or the last 20 years. And you can be mindful that people might be storing things that aren't, English characters. All right, and then timestamps and dates. Oftentimes internally, you would represent these things as just the number of microseconds or milliseconds since the Unix epoch. Sometimes some systems have their own internal date format or timestamp format, and then keep track of time zones or not, right? This varies per system. But the one I want to spend a little time talking about is the difference between floating reals and numerics, because this is a good example where the database systems are going to do a bunch of extra stuff to make sure your data is actually stored correctly in the way that you expect, even though it may not be the fastest way to do this, because the hardware can do things much faster than we can, but we can guarantee that we don't have any loss of data or loss of precision in what we're storing. So for variable precision numbers, this would be like what we call the floating point numbers. So these are, again, think of this as using the native data types you would have in C or C++, like you call float or you call double, right? And that's in the code. That's defined by the IEEE 754 standard. And this is what most architectures are actually going to implement. And then because they're also going to have specific instructions that can operate on these data that is really, really fast. But the problem is going to be that, again, they can't guarantee that they can store exact values. So the example I always like to give is something like this, right? You have some simple C code, and you want to store two floating point numbers, X and Y, 0.1 and 0.2. And so if I run this code here, you get output that looks like this, right? It looks like as I would expect, right? That I can store X plus Y, I would get 0.3, follow a bunch of zeros. Same with just storing 0.3 by writing out 0.3 by itself. But if I change the precision of basically the number of decimal digits I want at the decimal point, like this, now you see you actually get widely different numbers, right? And neither one is exactly 0.3, right? And this is because the way the hardware is going to store these floating point numbers is using variable precision, and it can't exactly store certain decimal values like 0.3, right? So even though, with a less precision in my output, it looks like it's the same, but in actuality, the actual bits in the hardware are not the same. And if I write this out to disk and I read it back in, and based on what calculation I'm trying to do, I may end up with incorrect results or unexpected results. And this is why data systems will maintain what are called fixed precision numbers, where the data system can basically keep track of where the decimal point is and the scale and other metadata about every single number that it's going to store. And then now I would store maybe like a string representation of the decimal, and then I use that extra metadata I'm storing to be able to interpret what that byte array actually means to guarantee that any calculation I do, I get the expected precision I would want on the results. Right? These are sometimes called fixed point decimals. Right? Basically the same idea. It's like where I'm doing decimal points, but I'm managing this everything inside the database system myself, because we can guarantee that we end up with correct values. So this is super important in things like certainly banking, time you're computing interest. You don't want rounding errors. Anything with like scientific instruments, you don't want rounding errors, especially if you're like sending a rocket to the moon or something, right? So that's why we want to be able to do this, and it's not, they don't take it lightly, or it's not trivial to actually implement these things to guarantee the correctness under all possible circumstances. So the example I always like to show is actually Postgres' implementation of their fixed point decimals. They have a data type called numeric. And if you actually go look in the Postgres code, this is essentially what it looks like, right? That you have this struct here, and it has a bunch of metadata about what what's going to be in a fixed point decimal, and then at its core, the decimal, the value itself is being stored as a byte array, and then all this additional metadata is then being used to interpret that byte array to generate the answer, to convert it back into its correct form that guarantees the exact value that you expect. And of course, now this means that when we want to do simple things like add two numerics together, right? It's not just calling number plus number an instruction in a register. We have to implement all this stuff ourselves. So this is the code from a Postgres a few years ago, but basically it's the same in the newer versions, to add two numerics. And you can see here there's a bunch of if then else's. We're checking to see, is the number positive? Is it negative? Is it infinity? Is it not a number? Right? And this is all code just to add two numbers together. And certainly this would be way more expensive to compute than just, again, calling the simple addition instruction on two data registers. This is something that you have to run all this code, but this will guarantee that the value you would get is what you would expect, right? All right, so the other thing we have to be mindful is how we're going to handle nulls. So there's basically three approaches, and as I said, the most common one would be in the header of every tuple. You have a bitmap that keeps track of what values you have within that tuple are null or not. And typically you just store this bitmap to be the same size as the number of attributes that you have, regardless of whether columns can be null or not. It's not worth the overhead of checking that as you're interpreting bytes. But this is the most common approach people use. One that's more rare is to do special values. You basically say within the domain or the range of values you could have for a given data type, you designate one of them to represent null. Right? So if you're storing things as 32-bit integers, 32-bit signed integers, you would say that the smallest value you could have represented by in32 min, you say that value is considered null, and so you prevent anybody from inserting that value. And of course, this means you have one less possible value you could have in your domain, but now you don't need to store that header per tuple. So this will be more common in column stores, which we'll cover in a few weeks. And again, you sometimes see this in memory databases as well. They're trying to reduce the size of the metadata they're storing per tuple. But for our purposes here, the top one is more common. The last one is to store basically a flag per attribute in the tuple to tell you whether this value is null or not, right? So think of if I'm storing a 32-bit integer, I had to have a 1-bit flag in front of that value for that 32-bit integer that tells me whether it's null or not. And of course, now as we talk about alignment, you can't just store things as single bits. You'd have to store an entire byte. So that means that I have to store a 30-bit integer has to be stored as 40 bits, right? To keep track of whether the first one's null or not. So this is a bad idea. I'm only bringing this up to say this is a possibility which you could do. But as we go out the entire semester, I'll try to put this little marker here to tell you, hey, this exists, but don't do this. So definitely don't do this. I only know one system that did this, and they immediately got rid of it a few years later. So this is a bad idea. If you have a row store, you want the first one. If you have a column store, you want the second one here. And then we have actually our own paper actually how to store nulls correctly in column stores. Again, we'll cover that more in a few weeks, but if you take the advanced class, we'll read this paper and go into way more detail about how to do it. All right, so before I say the assumption that we're going to say that a tuple has to fit into a single page, of course, now if I have to support really large attributes, this is not going to work, right? If my attribute I want to store is larger than my page size, what do I actually have to do? So this is where overflow pages come in. The basic idea is that we can have separate pages where if the value of a given tuple is larger than I can fit in that page, then I have a separate page where I put that value in, and now within my tuple, I store a pointer, basically a record ID, to that other overflow page. And then now as I'm scanning the data, I'm going to interpret this data within a tuple. I know I've come across one of these pointers to this overflow page. I no need to follow that to get the original data. Right, so I say this contents attribute in this table here is too big. So I have an overflow page where I'm just going to store all this variable data. And then now within my original tuple, I'll store the size of the data and then the page number and offset, like a record ID, to where to go find this overflow page. So different database systems do different things to interpret, to trigger when you store things in overflow. So in Postgres, by default, if the anything you try to store is larger than 2 kilobytes, even though they have 8 kilobyte pages, they put in the overflow page. In MySQL and SQL Server, and I think Oracle as well, if the thing you're trying to store is larger than half the page size, or larger than the page size or larger than half page size, then they put it in the overflow page. There's a bunch of optimizations we can do to mitigate the overhead of trying to fetch these pages. So we can take these overflow pages and compress them using like Snappy or gzip. Again, we'll cover that in 2 weeks. Another technique is called German strings. This obviously comes from the Germans, where in addition to the size and offset that I store in the original tuple, I can actually store a prefix of the value. So if I'm just trying to do string matching, where like find all records where the contents field starts with the word Andy, I could check the prefix in the original tuple and see whether I have a match there before even following the pointer to go catch the overflow page. Again, it's back to this idea we said at the beginning of like trying to avoid having to read data from disk that I don't actually need. If I spend a little storage overhead of storing things in a prefix, can avoid me having to go do that in certain situations. Right, and if the data I'm storing in my overflow page is too larger than the overflow page, I can just again put another record ID at the end of it or the front of it to tell you where the subsequent page can be found. So I can chain these things together to reconstruct large tuples. In some systems also too, you can actually represent data in pages that are not managed by the database system. These are called external value storage. So this would be like if I have a 20 gigabyte movie, I don't want to maybe put that in my database system, but I want to still have the database system be aware of that this data exists. So I could have a record that has essentially a URI or pointer to some external storage that's managed outside the database system, that if I need to, I can suck it in, read it, and hand it back to queries. But the responsibility of maintaining that data, making sure that it's transactionally safe, and making sure that it is the data system is going to, any guarantees it would have for making sure the data is durable or it's safe on the regular data, it's not going to guarantee those things, but it still allows me to stream data out and fetch it, serve it into tuples as needed. So not every system supports this. Oracle calls them B files. Microsoft calls them file streams. It's basically a way to store large files outside the data system, but then still suck it in if you need to. And there's a paper from a few years ago. Actually, it's over. It's 20 years now. From Jim Gray, the guy that went at 21 databases, where they examined whether you should put things in the data system or not. I think their recommendation was like anything larger than I think it was like 128 kilobytes should be external, less than that internal. I don't know if that's entirely true anymore, but people have thought about this problem, like when should you store large things in the database or not. In general, database systems usually run on more expensive hardware, so you don't want to store like massive files. And something that's external value storage is a way to sort of get around that. So it looks like it's in the database even though it's not. Then you can put it on cheaper storage. All right, so we've covered a lot. Fat Face Rick is still not out of the hospital yet. So I gotta go figure out where he is. But we've covered database storage, the basics of it. So again, database system is basically a collection of pages that can be stored on disk or some non-volatile storage. And then we'll have different ways to keep track of where those pages are located. And then we'll have different ways to store those pages on disk, whether single file, multiple files, or whatever. And then we have different ways to store the tuples that are inside those pages. And then again, because of this layered architecture.
Number 169. Please go to position to ticket number 350.
That's not fabulous, right? Okay. Because we have this sort of layered architecture, the other parts of the system don't need to be entirely aware of, like, oh, this is actually how I'm storing things like in a slotted page architecture or not. All that is abstracted away, and then we can still, we can change things out and modify them and extend them or enhance them as needed without worrying about breaking the entire system. It's not always the case, but then ultimately that's the goal. Of course, there's a trade-off by having too much abstraction that makes things inefficient. But again, it depends on the limitation, and we'll see when we want to relax certain guarantees or certain restrictions later on. All right, so again, today's class is about how to represent data as a database of files on disk. Next class will be then how we then talk about when we bring things into memory, how do we keep track of that? How do we then hand off those pages of memory, those pages we brought into memory to other parts of the system? Then how do we make sure that we write them out in a timely manner, in a safe manner, so that we don't crash and lose anything. Then after that, we'll come back and talk about different ways to store things on disk again. But we're going to cover the buffer pool manager, the memory stuff first, because you're going to need that for project 1 that'll go out next week. Okay.
Money, flick, flips, acrobats over tracks. Cash money, flick, flips, acrobats over tracks. Cash money, flick, flips, acrobats over tracks. Cash money, flick, flips, acrobats over tracks. Get the fortune, motherfucker fame. Maintain but never strain, flow with the grain. Get the fortune, motherfucker fame. Maintain but never strain, flow with the grain.